let's get started. Um, does does anyone have any question to ask about the last lecture or anything? Um, by the way, some people were asking like where the videos are. I think it's uploaded to the course website. Like if you go to course website, I think you will find the lecture notes and also the videos. Yep, okay. And I think it was recently posted to YouTube too. So if you go to YouTube, you probably can see the same thing. So regarding the lecture materials, does anyone have any questions? Vincent, did you get a chance to look at the video? So do you have any questions since you missed out the class yesterday? Okay. Okay. So yesterday was a theory class, and today is the lab session. So the idea is I would like to show you that both mathematics and computer programming are very important to quantitative trading. Um, and today we are going to do some programming. We're going to introduce. Well, first of all, we want to tell you like why computer programming is important, and number two, we want to show you some basic Java programming. And number three, we want to show you some basic math programming using Java. And then finally, we want to co-op some strategies for backtesting. But this is a hands-on session, so it will take a lot of time. So we'll see how far we go. But first of all, uh, has everybody installed Labin and Algo Quant on your computer? Because we are going to use this software for experiment purpose. Has everybody installed it? Okay, so you guys are able to run the Maven test and pass everything. So you make sure that like you install everything properly. That was a question actually. Okay, that's very good. Okay, so let's get started really. Okay, so today is about programming and backtesting quantitative strategies. The focus is on how do you program a mathematical strategies using algo quant. And algo quant is a quantitative trading research toolbox, and we are going to see what that means momentarily. Um, okay, so first of all, we want to understand why technology is important in quantitative trading. Okay, like traditionally if you're doing like value investing or the, I don't know, or trading macros or trading based on gut feelings, uh, you don't need a lot of programming. So you just some sort of a simple models. You may program it in Excel. In fact, a lot of like analysts they program their models in Excel, so they are able to say rank the stock to decide which one to buy and sell. They don't require lots of programming, mainly because, for example, as far as I know, like analysts, they do not do a lot of backtesting. Um, but for quantitative trading, as we discussed yesterday, after step one, the modeling step, in step two, we need to co-op the quantitative trading strategies. Um, and the source code is used in multiple places. For example, it's used in sample and outsample backtesting. Um, and we discussed this. Historical P&L is not an indicator for trading for deciding to trade a strategy or not. We want some sort of indication about the future performance. So in that case, let's say if you want to compute expected P&L, we would want to do some uh, simulation on bootstrap data. Um, so that requires also computer programming. You need to code up your strategies. And after that, we also want to do some parameter calibration. So the idea is like, let's like in the moving average cases, um, we have two parameters, and we need to find out what the optimal parameters are. But in general, we will not be able to do it analytically. So we have to resort to computer simulation or computer optimization, for example. Uh, One classical example is portfolio optimization. We recently did a project for a hedge fund. So basically, we provide them with an optimizer to optimize a portfolio of like thousands of stocks, subject to many uh, constraints, realistic constraints, and that require heavy programming because basically we produce an optimizer just for this particular problems. Um, another area using programming is sensitivity analysis. Let's say you somehow come up with optimal parameters, but in VR, let's say the parameters are say 2 and 1, okay? But these are the but but in reality, like when you're trading in the future, the optimal parameters are not going to be 2 and 1. Hopefully they're going to be somewhere around that. For example, like 2.5 versus like zero point 0.9 or 2.1 versus like 2. So when you are actually trading in the future, you never know what the optimal parameters for the futures are. Okay. We hope that like after all the parameter calibration, we will end up somewhere close to the future optimal. Okay. But then the idea is like if the future optimal is a bit off from our optimal values, or put differently, if our optimal values are slightly off from what the future optimals are, how would that affect our P&L? So that's sensitivity analysis, and that's very important. Now, if your optimal parameters land in a plateau, then you're pretty safe to play the strategies using this set of parameters, because you know that even though the real optimal parameters um, are off by a little bit, your P&L remains more or less the same. Okay, but if there's a sharp difference between 2 versus 1 and 2.1 versus 1.1, let's say if 2 versus 1 you make a lot of money, but then 2.1 versus 1.1 you lose a lot of money, then you know that like your strategy is very sensitive to the parameters chosen. Then it might not be a good idea to play these strategies at all. So the idea is that you need to do sensitivity analysis to see how the P&L how the strategy performs around the optimal parameters you have chosen, and see if you're landing a plateau. If not, if yes, then okay, you may be able to play the strategies. Otherwise, uh, the strategy is too sensitive to the parameters chosen, so you may not be able to play it. And finally, um, last but not the least, you want to use the same piece of software that you use for backtesting in live trading. As discussed yesterday, you do not want a translation between research code and live trading code, because it's subject to uh, a lot of possibility of translation errors. So in that case, whatever you're trading in production may not be exactly the same as whatever you are backtesting. So that would means your research is not very meaningful, or it means that you're playing a strategy blind. You're trading a strategy you didn't really research. So ideally, the same piece of software for research should be the same piece of software for live trading. Okay, as you can see, like even from the research to the live trading process, we require computer programming, and it's very important. Okay, um, so computer programming skill is very important. The idea is like this is a recurring theme in this class. Um, um, Technologies or software are weapons in this financial trading warfare. Okay, the more effective the weapon that you use, uh, the more money you are expected to make. Yeah. Okay. So efficient and effective use of a technology is very important in your research process and also in your live trading process. Okay. Like so what does a trader do? What does a quant trader do? Okay. Now this is the ideal case. Okay, this is not reality. This is just the ideal case. Ideally, the traders should be doing what they're supposed to do. Okay, like coming up with trading ideas. Okay. After they come up with ideas, then they can quickly prototype it. Okay, they produce the software, they produce the strategy code. Okay, that they can just fit into a computer system and automate everything that we just discussed. Okay, so you see, in fact, like this example, outsample backtesting, computing P&L properties, parameter calibration, sensitivity analysis, they are all mechanical tasks actually. Like they're all mechanical tasks. They are really no brainers. Like for every strategy, they are more or less the same. Okay. Um, so ideally, you should have a computer system that can take your strategy code and just produce a report for you. Okay, and then you read the report and say, oh, okay, check. These are good. Okay, then we decide to go ahead with this strategy. And if the report say, oh, the PN is crap, and then the mass drawdown is too much, then you say, oh, this strategy is bad. Then we go back to dreaming up another ideas, or we iteratively refine the ideas and produce another prototype, and then we fit that into the computer system again to automatically produce this report. Okay. So in the ideal situation, the trader should spend like most of the time, say 90% of the time, just coming up with ideas, and spend as little time as possible in coding. Okay, maybe he needs to code his strategies. Okay, but then like the rest should be done by a computer system. Okay, so maybe say 90% of the time, the traders are just like reading books, reading newspaper, talking to friends, just to come up with trading ideas. Okay, and then maybe like 10% of the time he spent coding up his strategies. Um, but then he should not spend a lot of time in like backtesting and all that because again, these are merging tasks. You need to have a computer system to do it. And as I said, this is the ideal scenario. Okay. Now, we mentioned that like we should spend most of the time dreaming up ideas. We should not spend a lot of time programming it. Now, but in order to achieve that, you need to be able to you need to be able to prototype a strategy very quickly. Say let's say you have a new idea, you have a new training ideas. You should not need to like code it up line by line from scratch. You should be able to have a lot of building blocks that you can put together to construct the strategies. For example, if you're building a mean reverting strategy, okay, so what goes into mean reverting strategies? So first of all, you need to be okay. Let's type it here. So for mean reverting strategy, right? What do you need? You need to have a basket that is mean reverting, okay, and then you need to have some way to check whether the basket is indeed mean reverting, okay. Okay, and then you need to be able to have a strategy that apply to and then you need to have a strategy F to play the basket. Now if you have like multiple if you have like multiple baskets, then you somehow need to do portfolio optimization among the baskets. Okay, so you need to do asset allocation. Okay, um or maybe some other stuff too. Okay, some other stuff. Now you see that like if you have to program like this brand new strategy from scratch, then it will take forever. Okay, because you have to program everything. You have to do the basket constructions. Okay, so this is basket construction, and then you have to have some way to check an indicator to indicate whether the market is now in a mean reverting regime or a trend following regime. Okay, and then you need to call up a strategy that plays the basket, and then you need to do asset allocation. Now again, you have to program everything like this from scratch, then it will take forever. Ideally, your research system should provide you with these building blocks. Let's say 4 building blocks that you can just put together to create new strategies. This this is this is this is the only way that can make your prototyping process very quick. Okay, so ideally your research system should be a toolbox that have many building blocks that you can put together, like playing Legos. Okay, um, so here is the some of the building blocks available in AlgoQuant. Like say, for example, they have a bull bear market indicators that's based on the conditional probabilities computed using some sort of very complicated differential equations. Um, and co-integration is a way for you to construct baskets. And then there are also some portfolio optimizers that you can use. So if you can just combine these building blocks together to build a new strategies from scratch, okay, without you programming everything from scratch. So again, what I try to say is, uh, creating a strategies should be just like playing Legos. All you need to do is just to put building blocks together to construct a new strategies. You should not need to program everything 9 by 9 from scratch. Okay, so this is the key to quick prototyping, and this is the key to success, as we shall see. Now we talk about the ideal scenario that the trader should spend most of his time like dreaming up with strategies. But this is what they hire for, right? I mean, this is what they're supposed to be best at. I mean, they're not programmers. We don't hire them for coding. But unfortunately, in reality, what you need to do whenever you come up with a strategy is like you need to do backtesting. And when you do backtesting, you need to say do data cleaning. You need to do data cleaning. I'm sorry. And then data cleaning is not easy. Data cleaning is not easy because especially in high frequency or intraday trading, uh, your data source is unlikely to be the timestamp are unlikely to be aligned. Let's say you have two assets. Okay, let's say you have two assets like x1 and x2. Now let's make it even more specific. Let's say the first asset is euro dollar versus dollar yen. Okay, and then you get a tick by tick data from say from Reuters, okay, or Thomson Reuters. Um, Now the war file, the source file, I mean the war file from Reuters, they just give you the tick by tick data with the war timestamps. Okay. Now if you want to trade a pair of this asset like euro dollar versus dollar yen, the timestamp are not aligned, so you have to write code to sort them out to align the timestamp for any synchronous backtesting, right? And then you also have to write program to read gigabytes of data. Now I can tell you that like back a few years ago, like maybe 3 or 4 years ago, uh 1 day worth of euro dollars traded on the Reuters platform is 1 gig. Okay, so for 1 year it's like 250 gigabytes of data, and you need to somehow process this huge amount of information, and that requires significant programming. And then you want to extract useful information from your data, like price earning ratios. Um, oh, another thing is like the world is not so perfect. I mean, even though you buy the data from Reuters or whatever other data vendors, there are going to be missing data. There are going to be outliers. There are going to be bad data. So you need to uh, write your own data cleaning code to handle these situations. So one way to handle missing data is to do a rollover. Okay, but there are other sophisticated ways to do missing data too. But we will not get into the details for the missing data handling algorithms. And then if your strategy is event driven, then your software, your code, your strategy code may also listen to some news and announcement. So for example, you may want to have a database of announcement schedules like FOCM meetings and stuff like that. Okay. And then finally, after you do all these preparations, you can start to code up your quantitative trading strategies. Um, after you code up, you do simulations, right? But what are you simulating with? You simulate with an order book, right? So you assume the bid-ask spread, and like, by the way, just because you want to buy something doesn't mean that you can buy those things, right? Because they're slippage. Like let's say you want to buy, and you put your order in the bid queue, okay? So you want to buy at the best bid, and so you are expecting the market to go up, right? You buy because you expect the market to go up, right? Let's say you put your order at the best bid. The market does go up, so the price goes up. But then the thing is like your prediction is correct, but your order is never executed. Okay, so it doesn't help to generate money. So there is slippage problem, and there are also some execution assumption in your order book modeling to determine whether your order is executed or not. So all these complicated simulation, right? Because you want to simulate your strategy as realistic as possible. So you want to have a very realistic simulation of the order book or the queue size and stuff like that. Okay. And in general, if you're doing intraday trading or high frequency trading simulation, then you need to wait for a very long time for the simulation to complete, for one simulation to complete. And this is especially true if you are using MATLAB or R, because this is script language. Okay. Um, so usually, just putting random parameters to your strategy won't make it work. Okay, so you need to do parameters, calibration, and then you do the simulation again. Now this is already a very moving process. Like, so one simple way to do parameter calibration is to do a brute force search. Okay, you search for you search among the space of possible parameters, and then you see which one which parameter set is the best, and then you choose that. Okay, this is a very dumb way, and it's not a good way to do it. But this is a very easy to understand example. Okay, the point is that for each parameter set, you need to do the simulation again, right? Because in order to come up with the historical P&L, for example, you need to do simulation. So if you have like, let's say you have like, let's say moving average crossover strategy, moving average crossover, the strategy we talk about. So it has two parameters, okay, two parameters, and let's say we limit the first parameter, the faster moving window to 1 to 5, okay, and then the second one 20 to 200. So we are talking about what? 5 multiplied by 180, which is what? 900. So we have 900 combinations of parameter to choose from or simulate. Because for each parameter set, for each particular parameter, for each pair or for each combination, we need to do a simulation to determine the historical P&L. Okay. Um, if you're doing intraday trading, each one, let's say each one takes I don't know, an hour. Okay. So we're talking about 900 hours here just to do parameter calibration and simulation to choose the optimal parameters for the historical data. Okay, now this is like forever. Okay, so we are going to solve that problem. Okay, so you wait a very long time, and the long time meaning like 900 hours in our example, for a simulation to complete, and then you choose your best parameters with respect to the historical data. Okay, if it doesn't work, then if the optimal parameter does not work for outsample testing, then you repeat the process again, and then you wait a very long time. Okay. Um, so these are all right, but what complicates the problem is really the bugs in your simulation strategies, in your strategy code. Like when you do this simulation, when you do this recalibration, often you find bugs in your software. Okay, you find bugs in your strategy code. So you debug it. Okay, and then when you debug it, you find more bugs. So you debug it again, and you debug it more, and you debug it even more. So you need to be patient, but then your patience runs out. Okay, and you become very frustrated, and you become very angry. And finally, you give up. You give up not because your code is correct, okay? You give up just because you're running out of time, your boss pushes you to trade, and for whatever reasons, you just give up, okay? And then you start to trade. So this is a very typical IT process for quant traders. I mean, ideally, we want to spend 90% of the time doing the mathematics or coming up with trading strategies. but in reality, you probably spend 90% of your time doing coding. And it's not even coding up the strategy, it's the coding up for things that are very mechanical, like handling missing data, like coding up the execution of the order book and stuff like that. Like in reality, like a quant trader like myself, I mean, like we spend like maybe like 90% of the time doing this debugging and programming. This is very annoying, okay? This is not like what it's supposed to be, okay? Um, so um, so it's true that like a lot of quant traders, they or quant analysts, they just work like programmers. They spend maybe like 90% of the time doing programming, and maybe only like 10% of the time doing the mathematics. In this is a very unfortunate situation, but that's reality. Okay. Now the reason for this sad reality is the research tool that people use are in general very primitive. For example, a lot of people use Excel, especially the equity analysts. Okay, they build their model of Excel, and some more sophisticated traders they use MATLAB/R or other scripting languages. Okay, um, there are also like commercial software that you can code up your strategies and do backtesting like MetaTraders. Um, the thing is like these commercial backtesters, they are not mathematical systems. Okay, if you have to code up a very sophisticated math strategies, they don't provide a math library out of the box for that. You may have to call a third-party math software like MATLAB or R for some external DLL calling. Okay, so it's not easy. Like the idea is like, in my personal opinion, okay, it's just my personal opinion. These tools are very primitive. They are not built for qualitative trading in terms of, in the sense that like it's very difficult for me to use these tools to build sophisticated mathematical strategies and do backtesting on it, especially for intraday or high frequency data. Um, Among all these tools, probably R and MATLAB are the most popular. Everybody, I mean, maybe 99% of the quant trader that I know use R or MATLAB. Okay, and there's a reason for that. Because let's talk about R exclusively. Okay, let's talk about R. Okay, because probably there are more R users than MATLAB users. Probably because R is free. Okay, you can download it from the R website. The reason why people use R for quant trading is because most people know it already. Okay, most people know it already. If you're studying statistics in school, chances are you will spend your 4 years in school doing R programming. Okay, and other advantages another advantage of R is that it comes with a huge collection of math functions for modeling and analysis. So we talk about like for example uh, in um, in mean working strategies in mean working strategies, you need you hopefully you have modules like basket constructions, asset allocation to build your strategies, and R has exactly that. R has a huge collection of math library that you can use and put together uh, to construct new trading strategies. So that's the reason that makes it popular. But are these reasons valid? Let's take a look. Okay, now people can, most students knows R, okay, but in fact I think there are like more Java, C Sharp, C++, C programmer combined than R programmers, okay. I think in Java programmer alone there are already a million people that can program R professionally, okay. So the other argument for having a huge collection of math functions, that's no but that's not exclusive for R, okay. Um, like if you use other programming languages like Java, C Sharp, C++, and C, there are also math libraries that are available for you to call. For example, numerical method in we market this Java library called Shanshu. It also have a huge collection of math library that you can use and put together to construct your trading strategies. And there are other vendors in C Sharp world. And C++ Boost library is free, and latly is also free. Okay. So whatever advantages that goes into R, the advantage is slightly losing out now because even for general purpose languages like Java and C Sharp, you also have a huge collection of math libraries that support these languages. Okay. But on the other side, there are a lot of disadvantages using R. Okay. There are too many. In fact, we're going to only touch some of them. So one of my biggest complaint about R is like it's very slow. Okay, because R is a script language, so whatever you call up, uh, the interpreter execute line by line. Okay, so this is going to be very slow compared to compiled uh, languages like Java or C Sharp. And there's also limited amount of memory. Like if you're using 32-bit machine, then the maximum of amount of memory that any process can use is 2 gigabytes. Okay, but as I just told you, $, on Reuters alone is 1 gigabyte per day. So there's no way that you can load up 1 year worth of data into the memory, let alone processing it or analyzing it. Okay, there's just not enough memory to analyze all these data together. Okay. Another possibility is that like we are now in 2013. We are talking about like grid computing, parallel computing, cloud computing. Okay, so we don't just run simulation on one CPU. We want to run simulation on thousands of CPU. Okay, um, and if you're doing a scripting language in R, and then the possibility of parallelization is very limited. Okay, I don't know anybody's programming doing parallel programming in R. I myself don't know how to do it. Um, like if you're looking at the option pricing, well, you all see that like computing power is very important. Like for example, when I work at an investment bank, for the portfolio for the portfolio of option pricing for pricing a portfolio options, and doing all this with calculation, um, we often resort to having like thousands of CPU computing for like 10 hours just to do portfolio pricing and the risk management. So you see that like computer we demand lots of computing power in options pricing. We also demand a lot of computing powers in quantitative trading strategy research, and ideally we should run it on a grid of computers and not just on your desktop. Okay, and definitely not on your notebook. Okay, because they don't have enough computing powers. And parallel computing is the way to go. But if you do it in R, then it's very difficult to parallel iCircle. Um, and the R IDE is very primitive out of the box. But recently there are more nice looking IDE for you to program in R. But in any case, the IDE that you can program in R is nothing compared to NetBeans, Eclipse, or IntelliJ that for Java programming. Okay, because it's nothing. I mean, you can just download out and compare it with NetBeans. You see that the IDEs are not on the same caliber. Okay, and there's no debugging tools for R. Like the most popular way to debug in R is to just print out the variables. Okay, and this is very bad. Or you execute it line by line. Okay, so this is the typical way to debug in R. You either execute the source code line by line and printing out the variables. Okay. Um, this is not professional at all. Like if you're a professional programmer, you know that like for professional debugger, you can do breakpoint or conditional breakpoints. You can look at the variables, examine the variable, change the variables, or you can look at which thread you're running. Okay, in case of multi-thread or parallel programming. Um, and also like the R script the R languages or other script language, they look more like C code. Okay, it's procedural languages. Uh, um, there's no one unique interface that you can reuse. For example, like how do you define a function in R? Uh, Different people define it differently in R. So the function that I define may not be able to use in your software, and the function you define may not be able to use in my R script. Okay, so they do not communicate. Like the source code, the R code from different authors, from different programmers, they do not communicate because there's no interface. Okay, there's no such concept as interface in R. I. But by the way, like I have to quantify what I said. Like there is some limited object-oriented programming support in R, but most people don't use it. Like most of the R code are written using procedural language. They're not written in any OO manner. Okay, so these are the advantages of R compared to the general purpose languages like R. But the biggest problem with R is this: you cannot make sure that your source code is correct. You cannot make sure that your code is correct. If you go back to the slide that I had previously, you start trading after you give up. After you start trading after you give up because you're so frustrated in debugging your code. I mean, this is not to say that after you spend long enough time, then your code is correct. This is not like that. Um, it's just like fundamentally, there's no way to make sure that your code is correct. There's no unit testing. There's no debugger. There's nothing. You just type it in and you hope that your code works. But it never happens in the programming world. Okay, it's not like that. You need software engineering methodologies and approaches to make sure that your code is correct. And in R, there's nothing like that. So the biggest disadvantage of using R in quantitative trading is that you cannot make sure that your strategy code is correct. That's the biggest problem. Because it's just so difficult to code up anything complicated in R. And you do not want to put $10 million on something that you are not certain, right? So this is the biggest problem using R as a quantitative trading strategy tools, in my opinion. Um, so why is the technology so important? Why like say the biggest problem in R is that like it takes forever to program it, and even after you spend forever programming it, you are not certain whether you're correct or not. Um, all all it amounts to is productivity. Okay, like let's talk about in terms of like AI languages. Like when you are trying to come up with a profitable trading strategies, all you're really doing is searching. Okay, like as in AI, artificial intelligence, all AI algorithms are search algorithms in some sense. Okay, so likewise in quantitative trading research, you are searching for a profitable trading strategies. Like if you're very smart, what that means. What do you mean by very smart? Okay, like what do you mean by very powerful AI machines? It just means that like you have the computing power, your brain, your brain can search for bigger space of strategies and you do it faster than everybody else. Okay, so you're a smart person because you search for a bigger search space and you search faster. Just like an AI algorithm, a smarter AI algorithm is nothing but a more computer software that search faster and search for bigger space. Okay, that's what really being intelligent means in terms of AI languages. Okay, so we see that like so you search for bigger space, and let's say this is the goal, this is your target. Okay, this is a profitable trading strategy that you are searching for, and if you're smarter than other people, then you have a better chance of coming up with these strategies. Okay, but if you're not so smart, so what do you do? So you rely on technologies, you would rely on weapons. So if I'm not so smart, then I search for a smaller space, and that may be very far off from the target, okay? And I search slower. But if I have a machine that allow me to search a lot quicker, so if I have a machine that allow me to do backtesting a lot quicker than a smart person, then my chance of coming up strategy is probably bigger than a smart person, right? Because I now using computer software, using technology, I can search for different part of the search space in parallel. Okay, even though like each time I search for a smaller space, but together I search for bigger space. So the chances that I land up on this target strategy, or the chances that I come up with a profitable strategy, should be bigger than a smart person without using technologies, right? So the idea is that like research tool is like weapons in a trading warfare. Like if you're a smart person, like back 30 years ago, you're a smart trader, like Warren Buffett, I don't know. You don't rely on technologies. So basically, you're fighting with your bare hand. You fight without using any weapons. You fight with your bare hands. Now, but then some people, so that might be all right. But when there's no technology when there was no technology available, okay. But as technology evolved, like you have Excel, okay, so you start programming up your models in Excel. So you do it faster than the guy who sits next to you, even though he's smarter, right? But you do faster because you have technology. And then you have like R and MATLAB that can do mathematical programming significantly better than doing it in Excel, okay? Because it has a huge amount of libraries that you can call, okay? So if look, comparing using R and compare using no technologies at all, okay? You fight with your bare hand. Of course, if you use R, you can construct a mathematical training strategy a lot quicker than somebody who's doing it using calculators, right? So, and then you have like other say MetaTraders, and then the idea is like if your technology allow you to do trading very quickly and it allow you to backtest the strategy very quickly and it allows you to construct a strategy very quickly, you should have an advantage over the guy who's very smart but who does not use any technologies. Okay, so technology changes the game of quantitative trading. Um, the idea is that if the smart guy spent 3 months coming up with a trading strategy, and you can spend like 1 month coming up with like 30 strategies. Among those 30 of them, chances are one of them is going to work. Okay. Another reason why you need to be able to another reason why you need to be able to construct and backtest a strategy very quickly is this. Um, you see that there's a trading opportunity right now in the market, okay? And then you have a trading ideas for that. Now, if it takes you 3 months to justify this trading idea, then the trading opportunity will be gone. So it's useless, okay? You want to be able to justify a trading idea in 3 hours, and then if it works, you start playing it, you start trading it to capture just the opportunity in the market right now at this moment, okay? So in that case, you also need to be able to construct and backtest a strategy very quickly. So in summary, we need a very good trading research toolbox that does the following. First of all, it allows you to code up a strategy very easily. Like say, for example, by putting up modules together, as in playing Legos, okay? And it should allow you to plug and play multiple strategies. In terms of backtesting, of course, it leads to simulate with historical data, but it also leads to simulate with fake and artificial data, like bootstrap data, okay? Um, and it also allow you to do control experiment. No, so it should allow you to set up like different order books with like different bit ask size, with different execution assumption, etc. So you need to be able to backtest with like different scenario that might happen in reality when you're actually trading live, okay? And hopefully all this can be done in a plug and play manner as an object-oriented programming. Also, this research toolbox should generate all the performance statistics like P&L, expected P&L, Sharpe ratio, omega, and blah blah for you as a trader to justify whether this strategy works or not. And then it also do this parameter calibration, sensitivity analysis. Um, Now, if this takes like 900 hours to do it, that's useless. Okay, ideally it should take like I don't know, maybe half an hour to do it. So in order to do this, you need to be able to do all these programming tasks on a grid of computers, on a grid of CPUs. So parallel programming is very important. But we as a trader, we are not programmers, right? We're traders, we're not programmers. Ideally, for all these things, the only thing that we need to do is step one, okay? The only thing we trader needs to do is coding up our strategies, okay? And nothing else. All these things should be done automatically by the computer system, okay? We should not need to program them, okay? Because they're the same for every single strategies anyway. Um, so ideally, this trading research toolbox should relieve you from coding all these merding and mechanical tasks. We as a trader should only focus on coding up the strategies. That's it. Okay. So you see that R or MATLAB provides nothing like this. In fact, most of the commercial vendors that provide backtesting tools provide nothing like this. Okay. You still have to spend lots of time programming it. So we are looking for an ideal trading research toolbox that um, elevate us from doing any of this mechanical programming. So the idea is like we want to feed the traders. The traders should not need to do any of listed on this page. The trader should not need to do lots of programming. Um, Calibration for parameters should be done automatically. Data cleaning should be just a tool that you can call. You do not need to program them ideally. Um, you do not need to spend a lot of time debugging. Like the amount of time you spend on debugging depends a lot on the tool that you use. Like back 10 years ago when everybody is using C++, you have to spend lots of time programming, say, memory leak, segmentation fault, and or whatnot. But when it comes to Java and the C Sharp, well, there's no memory problems. So that probably takes away like at least 50% of the debugging time. Okay, when there's no memory leak, and there's no segmentation fault, then you don't need to debug for them. So in Java, there's nothing like this. So that's why like the productivity using Java is 10 times, at least 10 times faster than the productivity programming C++. Okay, we see that there's a progress in technologies. Okay, so we now we want to go get into the programming session now. So we need to do some hands-on lab. So can everybody fire up your lab beans just to make sure that it works? Okay, can everybody do that? So if you fire up your lab beans, you'll probably see something like this. Okay. Um, can everybody see my screen, my lab beans? So if you install your algo quant properly, you probably will see something like this. You see algo quant demo. Is everybody able to do that? Oh, that's great. So everybody have your lab beans launch. By the way, let's do a poll. How good is everybody's programming skill? Is everybody able to program in Java, or is this your first time? Oh, okay. So everybody have some sort of programming experience. So we do not need to get into the Java basic, right? So in this case, we don't need to do that. So everybody agree? Okay, so that gives us actually more time to play with the real stuff. Okay. Um, let's do a simple experiment first. Like we talked about Markov chain. Um, we talked about Markov chain yesterday. So let's do some experiment on Markov chain. Um, Now if you go to Google and search for Shanshu examples. So if you Google this keyword, okay, Shanshu example, you should see a lot of examples using Shanshu, and one of them is Markov chain, Markov models. So if you go to this website, everybody able to go to this website. Do you see the source code for doing Markov model? Okay. So now, I just want to make sure you guys are still seeing my lab beans windows, right? Not the PowerPoint, but you are watching my lab beans. Okay, good. Now you see that like Markov model. So basically, um, I copy and paste the example I just type here, the link from the link here to here. Can you see whether you can run it? So the way you do it is like you copy and paste it, right? Maybe you fix the imports. So the way you fix the import is this. You just hit Control Shift I, and then you hit OK. So you fix the imports, and then you try to run this program. And you should see some output. Uh, so please try this to see whether it works first. Okay. So this shows you that we can actually do mathematical programming in Java using statistical or the algo quant library. We going to demonstrate this using a very simple Markov chain model. So everybody is able to run this uh, because we're going to do some experiment on it. I'm going to explain this example after you're able to run it. Please let me know after you type it, okay? Yeah. So what I would actually suggest you to create a new package first. So if you open up AlgoQuant demo, you can right click on say here and say new package, and then you can type in a new package name called say CQI, okay, and then you hit OK. And then after you have this empty package, you create a new class, and then you say Markov model, okay. You create a new file like this, and then you just copy and paste the code here. Yeah, you need to change the package name here as well. So this package name needs to match whatever you type here. And then you delete the import, and then you hit Control Shift I to do the automatical import. Please let me know after everybody finishes this. Okay. After you finish this, please let me know. Okay. Well, thank you. Wait for more people. Please ask question if you have any. Okay, please raise any question that you might have. So everybody able to copy and paste the code and run it? Oh, that's a good question. I think um, I think they have a way for you to download. Like if you scroll to the bottom, uh, it says plain text and original format. If you hit original format, you can just download the code, the original Java code. If you hit plain text, you can download as a text too. Okay. Hector, um, are you alright? Do you need any help? Okay, great. By the way, do you see my Microsoft Paint screen? Okay, good. Okay, forgive my my drawing. Okay, so everybody able to run this, right? So let's delete some code, okay? Because we are going to do a very simple the classical version of hidden Markov chain, the webinar version of HMM. So we are only going to run this webinar HMM function. So you can delete lots of things. So I keep only, you see here, I keep only pi A1 and B1, okay? Um, and then I delete so for the continuous HMM training I deleted it. So not to cause confusion, okay? So I'm only going to run one this example, okay? And I'm going to show you why this example is interesting. So basically this is the two-state model. Let's see, I can draw better. Can you draw a circle here? Oh, okay. So this is the two-state model, okay? With transition probabilities. So no, okay. So basically with transition from state 1 to state 2. How do you draw a curve? this. Okay, so what this means is like here the transition probability is 0.8. I'm sorry, 0.2, and here the transition probability is 0.8. This is what that this is not a this is not what A1 matrix is saying. It's like from state 1 to state 1, the transition probability is 0.8, and then from state 1 to state 2, the transition probability is 0.2. So likewise, from state 2 to state 1, the transition probability is 0.3, and then from state 2 to state 2, the transition probability is 0.7. Okay, so this is what this A1 matrix is saying. This is the transition matrix for this two-state Markov chain. Okay, and then the B1 matrix is saying is just to remember the conditional distribution that we have yesterday. So you have a distribution, right? Conditional upon a state. Well, this is supposed to be a distribution curve. But in this case, we don't have a continuous distribution. We have a discrete distribution. So it looks more like histogram. Okay, so this is omega 1, omega 1. This is omega 2. This is omega 3. Okay, and the probability of seeing omega 1 is 0.8. And the probability of seeing omega 2 is 0.1. 0.1. Okay, and likewise, you have omega 1, omega 2, omega 3 here too. You can imagine omega 1, omega 2, omega 3 are the three possible prices or three possible return direction. For example, this could be like a positive return, zero return, and negative returns. And likewise, you have the same thing here. Except the probability is like 0.1, 0.1, and 0.8. Okay, so positive return 10%, zero return 10%, and negative return 80%. So you can imagine this is what this Markov chain is about. Okay, it's not easy to draw in computers. Okay, so everybody understand what this Markov chain is about, right? So the first thing that we need to do is like we do a simulation of this Markov chain. So basically, a Markov chain is it's just a random number generator. The way you see this is a random number generator is this. Okay, you randomly end up in one state, and then you pick an observation. So let's say you end up in this state, you have 80% of the chance to pick omega 1. And then next time step, you can either stay in this state, or you can with 20% probability of going this state. Let's say you go to this state, you have like 10% of probability picking omega 1. So you can see that like it will generate observation like omega 1, omega 1, omega 1, omega 2, omega 2, omega 3, omega 1, omega 1, and then going back here, omega 2, omega 2, omega 3. So you see that like a Markov chain is just a random number generator. Okay, so we can generate, say in this case, we generate 10,000 observations of this simple two-state Markov model. Okay. So one way that you can see it is like you first of all you put a breakpoint here. Okay, just the line after the observation, and then you do debug, and then you can see the observations of this hidden Markov chains. Now you move your mouse over here, you can expand it. Now you see like we generate 10,000 observations from this Markov chain, and you would expect to see, let's say, so these omegas are represented by 1, 2, 3. Okay, so this omega 3, omega 3, omega 1, omega 1, 3, 1, 1, 3, 3, 2, 2, 1. Okay, these are randoms. So these are the observations. So you can imagine this is saying, okay, price going down, down, up, up, down, up, up, down, 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 neutral, up, 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 like this. Okay, so you can imagine these are the observations that you see. Okay, the prices that you see. Everybody can run this and debugger and generate it. By the way, so if you I said this is a random number generator, right? So if you generate it again, you should have different set of observations. So let's see. Okay, so this is the observation I generated in this run. Okay, so we put it here, and let's try again. So I stop the simulate, I stop the debugger, and then I rerun it. And again, I look at observations. You see, this is generating a whole new set of observations. So we have 3, 3, 1, 3, 3, 3. Here you have 3, 3, 1, 1, 3, 1. Okay. So you see that so a Markov chain is just a random number generator of observations. Okay. Now, so here, since we are the creator of this two-state Markov chain, you know exactly what the specifications are. So these are the specifications. You have the initial state probabilities. So you have 20% chance ending up in state 1 and 80% of time ending up in state 2 initially at time 0. Okay, and this is the transition probabilities. These are the observation probabilities. Okay, now since we are the creator of this Markov chain, so we know exactly what the specifications are. But in general, you do not know that. Like remember, yesterday we talked about this GMA2 one model. In general, we can only observe the prices, and we often have to estimate the parameters. Okay. Um, so here we show an example of estimating the parameters for this simple Markov chain. Okay. So we don't know what the parameters are. We can only make some guess. Okay. So we guess let's say the initial state probabilities are 0.5, 0.5. Because we have no information, right? So we just say, oh, they're equally likely. So we say 50-50 for each of the states, okay? For both states, 50-50. And then again, we have no information on the transition probabilities. So we just say 50 and 50. So 50% of the time I end up in the same state in the next time step, and 50% of the time I end up in the next state at the next time step, okay? Because we have no information. And these are the observation probabilities. I just put in some random numbers here. You can put in other random numbers if you like. Okay, you can put in your own numbers if you like. And then I call this webinar models. Webinar is probably the first hidden Markov chain algorithm for parameter estimation. So I basically I put in the observations like the returns, okay, and then my initial model. So this is my guess of what the parameters are. I don't know what they are. I want to find them out. But I put in my initial guess, okay, and then I train this HMM say for 100 times, okay, and then I get a model. I get a trained model. So this is the model that we use for trading, okay. And then we try to compare this estimated model with the real model, okay. So I hit run. So this is my estimation from my observations, and then you compare them with this. Okay, so this is the transition probability. So 0.79, 0.8 more or less the same, 0.31, 0.3 more or less the same, 0.2, 0.2, 0.68, 0.7. Okay, so it shows that like the estimation of the transition probabilities are okay, good enough. And likewise, if you compare these observation probabilities to the real observation probabilities, they're more or less the same. Okay, so this shows you that well, first of all, the webinar algorithm works. Okay, um, the webinar algorithm works. Now, why are we doing this estimation? Again, in reality, when we are doing actual trading, all we observe are the prices. Okay, all we observe are the prices of all the returns. Okay, so these are the prices or the returns we download from say from Yahoo data. Okay, um, we never know what the true model is. This true model we never know. So this is the real market, but this is something that we never know. So we cannot use these real parameters in trading. The next best thing that we can do is that we can only estimate what the parameters are. So these are our estimation of parameters. So we need a very good algorithm to do the estimation. And one very good algorithm is from Webinar. Okay, so this is the Webinar algorithm that estimate for discrete models. Okay, and you see that the estimated parameters match closely with the real models. So we do not use the real models in trading. we use this in trading. Okay, we can only use this in trading. Okay, so you see, this is why we are doing this. So given the prices or the returns, we estimate a two-state Markov model, and then we use these parameters for trading. For example, we can use this for our GMA2 model we discussed yesterday. Okay. Now, for experiment, so I would like you to spend some time. You do two things. First of all, you create your own Markov chain model. So you change the parameters here. For example, you can create a three-state Markov chain versus a two-state Markov chain that I had here. Okay, or you can change the parameter. You can change this to like 0.1, 0.9, or 0.3, 0.7, something like this. Try to have your own um, transition matrices. Try to have your own observation probabilities, and then try to create observation. Do it multiple times to get a feeling of how Markov chain works. Okay. Now you see that like, you see how important it is to have a software now. Now you have a software to do Markov modeling, so you can generate as many observations as you like, and then you can get a feeling of what these observations like. Do they agree with the transition probabilities, or do they not agree with the transition probabilities? Um, or try to put some extreme values. Like I can have like 1.0 here, and all these are 0. All these are 0. Like what that means is like I always generate omega 1. Okay, if I get into state 1, I always generate observation 1. So I can likewise, I can have like 0 here. I can have like 1 point here. Okay, so try to put in some extreme value to see how the Markov chain behave. And the second thing that I would like you to do is that you do the estimation. You do the estimation, okay, to see whether the estimated results matches what you put in here. Okay, most of the time they are. The important question to ask is, under what conditions, under what parameters will the estimated model matches the true model? Okay, so try to ask yourself these questions. I'm going to ask you this question later, maybe in 20 minutes or so. Okay. Um, um, like let's say if I don't have enough data, do I get a good estimation? Or if I do not have enough training, say if I only train it for 10 rounds, do I get a good model? Do I get a good estimation? Now, or does this webinar algorithm works only for two-state model and it fails for three-state model? Okay, so you need to ask yourself this. So I would like you to spend the next 20 minutes or so doing this experiment. Okay, so try to program it up. Try to program this yourself. Use different parameters. Uh, generate different observations, and do different estimations to see ultimately whether the estimation matches the true values. Okay, and then we're going to have a discussion on this later. Everybody understand the this lab? Everybody understand it? Or do you have any question? Vincent, do you have any question? Do you understand the task? Okay. So okay, now it's now 9:20. So let's say I don't know, like 9:45. We're gonna have a discussion on Markov modeling and programming. Okay. I'll be here to answer questions. So if you have any question about the Markov chain or about programming, let me know. You can actually share your screen with me so I can actually see what you're doing, and then I can better help you. Okay. Okay. So the task to do is this task. By the way, are you able to see the note that I'm typing? Okay. So you generate different observation using your own Markov model, and then do estimations given different parameters. Check whether the estimated model agree with the real model. Now, again, the real model, you never know, okay? In reality, you never know. But since we are doing experiment and we create a Markov model, so of course we know. So, and then the question you want to ask yourself are this. The question you want to ask yourself are this, okay? When is the estimated model matches the real model? Now, this is an important question, right? Because ultimately, when we are doing doing real trading, we can only rely on the estimated model. We never have access to the real model. So we want to understand how good our estimation is. Basically, we want to understand how good a model that we can build. Because ultimately, we rely on it. We put real money on this. So we need to have some sort of assessment of how good um, our model of the market is. Okay. So this is an important question that you want to find out by doing this lab. So I will encourage you to say, for example, uh, put in extreme values such as 1, 0, blah blah blah. Okay, and then see how it behaves, how the Markov chain behaves um, uh, in stress scenarios. Okay. Vincent, what do you mean? Yeah. Okay. You see, this is what we talk about. When you create a new package in Java, um, you need to make sure that this matches where the uh where uh the one that you type in here. Okay. So say maybe you delete, like as Hatter suggests, you delete this and you type this. So you see here. Okay. So basically, like you have to specify the packages. You have to specify the package where the file is actually is. Yep. So Vincent, have you received the email? Okay. Well, let me know if you if you don't know how to use the license file. So basically, you just copy and paste. You just copy and paste this one to wherever your current existing license is. Hey, by the way, did you send CQI your MAC address? They should have already sent you a license, a long-term license for this course. So did they send you a long-term license? You should replace that. You should replace that long-term license with the one that you download. Then you will have no problem. Oh, bummer. Okay, I'll check. I'll check and get back to you. They should have sent you one. So Hector, how's your experiment going? Ah, so what's the problem? Okay. Well, again, the key is to find out from the experiments when the estimated models is good enough. Okay. So uh, that's the main point of this experiment. Because I mean the estimated model does not necessarily match the real model. In which case, we cannot use it for training purpose. So we need to get some sort of ideas of the estimated when the estimated models are useful and when they are not. Oh, great. So Vincent, you are ready to do some experiment. So please do this. Please do these things. Okay. Try to change the numbers, change the parameters. Um, try to create your own try to create your own Markov chain. Say for example, from a two-state model to a three-state models, and see how the estimation goes. Okay. I'll try to create some very weird uh, transition probabilities like zero, for example. Or you can have a sink state. Once you get in, you cannot get out, or something like that. So try to use some imagination, right? I mean, we talked about last time. Creativity is very important in quant trading. Imagination is also very important. So try to use your imagination to create some very strange Markov chain to see how the estimation procedure behaves. Okay. How's the experiment going? Shall we have a discussion now? How's the estimation? Um, did anyone create a three-state Markov model or even a four-state Markov model? Did anyone try that? Vincent, Vincent, how's the experiment going? Hector, is everything working? Okay, did anyone get a case where the estimation failed? Is anyone able to generate a test case that the estimation failed? The one that you put in is the real model. Like everything that you put in here is the real model. The one that you use to generate observation is the real model. So these are the real parameters, and you see this is the line. This is the line that we generate the observations. Okay, so this is the real model because it used the known parameters, pi a1 b1, which are here, pi a1 b1. Okay, so these are known values. So this is the true model. So the observations are always generated by the real models, and then we use the observations to generate an estimated model. Okay, just like in trading, the prices are always generated by the market, the real model. The real model is the market, and then we use the prices to generate an estimated model that hopefully matches the real market. So this experiment is to ask you when the estimated model is good enough, uh, is close enough to the real model. Does that make sense? Okay. So Vincent, are you able to generate a case where the estimated model does not match the real model? So you notice that like in this case we are generating 10,000 observations. Um, did someone try fewer observations? Like if you put in 100, what happened to the estimation? So try that, try that. It's very important. Okay, let's take a poll. Time. Everybody see the poll? Yeah, that's true. Yeah, in general, the estimation will be less accurate when there are fewer observations. Um, because like in statistics, most of the algorithms are really about convergences. So when n goes to infinity, then the theoretical result, uh, in theory, the estimation would match exactly the real values. But that's only when n goes to infinity. So I would like to point out one thing. Um, no. I mean, in general, this is a very difficult question. You don't know how close. That's the problem. You don't know how close your estimation is to the real models. Um, you can check the likelihood of a model, uh, uh, but that's only when you're comparing a few different models. Let's say you have 5 different models to choose from. You often choose the one that with the maximum likelihood. Okay, so that's as the maximum likelihood estimation. But ultimately, you would not know how close your model is to the reality. You never know really. Well, the reason for that is that you don't know what the reality is, right? You only have the estimated model. I think in statistical theory, in general, you given a model, you should be able to compute the probability of generating the observations, as in hypothesis testing. So in this case, given an estimated model, you should be able to compute the probability of generating the observed values from this particular estimated model. So you can quantify the likelihood of that. And in fact, this is the philosophy behind maximum likelihood. The likelihood is exactly the probability of sealing the observations from any given model. Um, the thing that I would like to point out is like there are few important things. Like if you have like 100 observations, then the estimation is not good. Um, well, let's see. I don't know whether it's good or not. Let's see. So if I have only 100 observations, oh, it's because I have extreme values. Let's see. What was the original value for this? Like point 8, point 1, point 1, point 2, 6. Oh, okay, sorry. How do I do that? So you see my screen now? Okay, so let's run it again with 100 observations. See, you see, like with 100 observations, the estimation is rubbish, right? So point A versus point 9, point 2 versus point 0.06, point 3 versus point 1, point 7 versus point 8. So the transition probability is rubbish if you have only 100 observations. Now, it's getting accurate if you have 10,000 observations. So let's try again with 10,000 observations. So it's 0.878, 0.2, 0.2. So with 10,000 observations, it's more or less the same. Now, this is really problematic, okay? Like in real trading, this is very problematic. The reason is the following. Um, how many trading? Let's say this is a model for daily returns, okay? So we are doing say daily trading. So how many trading days do you have in 1 year? 250, okay? So how many you have in 10 years? In 10 years, you only have like 2,500 data points. So how many years of data do you need for 10,000 observations? You need 40 years. 40 years. Most of the assets don't last that long. I mean, we don't have data for most stock for 40 years, okay? Because most company close down in 10 years, something like that. Um, so uh, like in practice, you need a huge amount of data to make the estimation accurate. So this is not practical. Uh, because again, like if you do daily data, you only have like 250 trading days in 1 year. So in 10 years, you only have 2,500 data points, and that might not be enough to estimate just for this simple two-stage model. This is a very simple two-stage model, right? But even that, you require a large amount of data to estimate it. So it's not practical in trading, okay? Simply because you do not have that much amount of data. Um, so this is some observation that you should be seeing from your observations. Um, the reason why this is so difficult, the reason why the estimation problem is so difficult and requires such a huge amount of data is because there are many variables in two-state model. Now the two-state model, the two in two-state model is very misleading. it looks simple, but in fact, this two-state model has a lot of parameters. It has like 1, 2, 6 plus 6. So there are 12 parameters in this two-state model. So there are 12 parameters in just this two-state model. So in general, as the number of parameters goes up, the more data that you need. So this Unison two-state model in fact has a lot of parameters. So I asked some of you to I recommended you to build a three-state model or even four-state models or increase the number of observations. Now in that case, you are essentially increasing the amount of you're essentially increasing the number of variables almost exponentially, okay, or very rapidly. In that case, the estimation becomes even more difficult, okay? So let's say you go from a two-state model to a three-state model. In that case, even 10,000 data points is not enough. You may need, say, I don't know, maybe 100,000 data point or even a million data point. Now in that case, you will not have that amount. You will not have that amount of data to estimate it. So this is a well-known problem in uh, in in using Markov model in trading. Um, Everybody understand this? This is really a take-home message for this experiment. Um, so offline you can do more experiment on your own by building different Markov chain, and then you see how well it converges. Okay. So based on that, is there any solution to this? Is there any solution to this? You see, like one thing that you can do is like you use a parametricized family of distributions instead of specifying observations like this. You see, like in this simple example, like 50% of the parameters, 6 of them, goes into specifying the conditional distribution functions. Now this is not good. Uh, Say if we use a parametricized families of distribution, we can reduce the number of parameters significantly. For example, instead of using 3 variables to describe a conditional distribution, we could have used a normal distribution. And normal distribution, it only takes 2 parameters, the mean and the variance. So in that case, if we have like 2 variance here, I'm sorry, if we have 2 normal distribution here, we only have like 4 parameters, 2 mean and 2 variance. So we reduce the parameters by 2. Now, Webinar algorithm does not work for continuous distribution. Um, there are other algorithms that estimate Markov chain model for continuous distribution. You can actually see it in the example here. So the first example is about discrete Markov chain, and the second example is about continuous Markov chain. And here you see that this is the three-state model. Okay, it's a three-state model. Uh, and the observations are specified by 3 conditional distributions. So this is the normal distribution, and each distribution takes only 2 parameters, the mu and the sigma. Okay. So you see that this is the transition probabilities. Okay, you still need the transition probabilities. You see that just by doing this, you are able to reduce the number of parameters in specifying the conditional probabilities. Okay, and then the algorithm to train this network is called so you have a function here that trains the continuous network. The Bum-Welch algorithm. So the Bum-Welch algorithm is the one that we use to train a continuous HMM. This is an EM algorithm. If you go to Wiki, you will find more information about this. Okay, so this concludes our exercise on doing this Markov chain. So the take-home message is that it's difficult to estimate for Markov chain, and as a trader, you need to be aware of the model. You need to be aware of the fact. You need to be careful about whether the model matches reality. You want to ask yourself this question. Okay. Any other question before we move forward? Okay. So the next experiment that we are going to do is back testing. So let's go back to our PowerPoint slide. So let's go back to the PowerPoint slide we have here. Okay. So we want to discuss how we can program our strategies and do backtesting on it. Okay. Um. Okay. So backtesting in algo quant. Um. Can if you go to like algo quant demo, can you open up the demo SMA2010 software the source code? Okay. Let's do this. So like if you open up algo quant demo and then scroll down, you scroll to this package crossover demo, and if you double click on this the 010 file, everybody see that? Just make sure you can run it first. So if you open up this file and right click on it and hit run file, are you able to run it? Are you able to build and run this file? So basically, okay, so it's doing some simulation. Okay, so basically this is simulating trading a simple moving average crossover strategies and on XOM. Okay, XOM is a stock uh, listed on MISC. So everybody see that? Okay. Do you see do you see the P&L curve? Okay, so basically this line is the stock price. Okay, you can move your mouse over it. You will see the price and the date and the timestamp. And then the blue curve is the P&L curve. You see this P&L is crap. Okay, and then you also see the buy sell signals. You can actually zoom on it. You zoom on it. Okay, and then you click on it. It tells you like say for example you're buying XOM at 28.77 for 2 units. Okay, so you're buying 2 units of XOM at 28.77. Okay, so you can zoom on it. It tells you it tells you the orders, the trading orders. Okay, and the bottom graphs are as you can see these are the graph for the long term, the longer term moving averages. I mean the slower moving averages and the faster moving averages. Like, can you guess which one is the slower moving averages and which one is the faster moving average? Can you tell just by looking at the curve? It should be pretty obvious, right? Because the slower moving average is the nice smooth curve here, this one, and the faster moving average is more zigzag. Okay, and you can zoom on it and see. So basically, this is a crossover, so it matches an order here. Okay. So here, the faster moving average crosses the slower moving average above, so you buy. Okay. So here's how you read this picture. Okay. So again, this is simulating a simple moving average crossover on XOM. This is the source code. This is the source code for it. If you close the window, if you close that P&L curve window, then you will exit the program. Okay. Now let's take a look at the structure of how we do backtesting in algo quant. Okay, and then we are going to write strategy. So first of all, you need to set up the data source. Okay, so all this is saying I am going to trade I'm going to trade XOM. So the product here, the product is defined here. Okay, so I'm going to trade XOM listed on NYSE, and it's a dollar-based instrument. Okay, and I'm going to simulate from 1990 to 2012. Okay, and I'm downloading the data from Yahoo. So AlgoQuant has a number of data source plugin, and the simplest one and the easiest one is the Yahoo data source plugin because it's free. So whatever stock that you specify here, it will download it from Yahoo automatically for you. Okay, so it makes it easy to do backtesting for those who do not have access to professional data source. Okay, so we use a cheap one. But only daily data is available for free on Yahoo. Okay, so this setups the data source is basically saying I'm downloading from Yahoo the data for XOM from 1990 to 2012, February the 2nd. Okay, and now you create a strategy. So this is creating a strategies. Uh, the SMA stands for simple moving average crossover. 2 stands for two parameters, the faster leg and the slower leg. So that stands for the faster moving averages is computed using the last 20 days of data, and then the slower moving average is computing using uh, last 250 days of data. So this is basically a moving average crossover strategy, one year versus 1 month. Okay, so this is creating a strategy. After you create a strategy, before you can simulate it, you need to create an order book. Okay, you need to create an order book to simulate a strategies. So this is creating an order book. A depth cache is essentially an order book. So it's creating an order book from the product. Okay, that we specify here. And then you can run a simulation. So basically, you create a simulator. You create a simulator, and then you create a trade plotter. A trade plotter is just a bookkeeping object that keeps track of all the buy and sell orders that you have in the simulation. And from the trade plotters, you can compute all the performance analysis that you want to do, like P&L, okay, information ratio. Information ratio is a Sharpe ratio, and omega. Omega is another measure that we are going to discuss in the last lecture. Vincent, you have a question? And then we print out the report here. Okay. The implementation of what? The strategy or the simulator? By the way, AlgoQuant is the source available software. So most of the stuff you have source code. For example, if you want to look at the strategy, so this is a definition of strategy. In NetBeans, what you do is that you right click on it and then you say navigate, go to the source. Okay, so this is the implementation of the SMA2 crossover strategies. Another shortcut for that is that you put your mouse over here and then hit Control B, and then it will bring up the source code for you. So this is the implementation of the strategy. We're going to look at it later. Okay. So in general, if you want to look at the implementation of anything in AlgoQuant, all you have to do is to click on it and go to the definition, or go to the source by hitting Control B in NetBeans. Okay. So this is the definition of a depth cache of an order book. Okay. Most of the sources are available. And then in simulator, you can look at how a simulator is coded up. Okay. The reason why we open up the source to the users of AlgoQuant is that first of all, they can independently verify our code, so that they have confidence in using the software, and secondly, they can modify to customize for their lead. Okay, so for example, if you do not like the way that we implement our simulator, you can create your own. Just make sure that it conform to the standard and the interfaces, then everything should work. Okay. Okay. Trade plotter again. You can look at the definition. So this is just an interface. You can actually look at a particular trade plotter. It's somewhere in AlgoQuant here. So you can search for it. The idea is like trade plotter keep track of a list of trade, a list of buy sell order that you generate during the simulations. And then from the trade plotters we compute the measures. Now there are many measures that we can use. Okay, profit and loss, cost P&L is important, but then there are lots of them. For example, you can have information ratio or Sharpe ratio computed using different definition of Sharpe ratio. You can compute mass drawdown, mass exposure, omega. Okay. By the way, the way you bring up this thing is you hit control space. Okay. You hit control space, and then you can bring up a list of possible performance measure that you can use. Okay. So this is really plug and play. So you can delete this if you don't want to compute omega. You just comment it out, or you can add another little measure just by this. Okay. Add. I hit control space, so it pops up automatically. These two tips. Hit enter and then new, and then say I want to do, I don't know, mass drawdown. Okay, I want to compute mass drawdown of the strategy. I can do that too. Okay, so this is how you compute. This is how you can plug and play different performance analyzer into algo quant. To I mean, you can add a whole bunch of lists. You can add as many as you like. Okay. Commission rate 0.5%. Let's say you can add a whole bunch of lists. So it goes back to what we discussed. So we need a technology that we can just simply fit the strategy code into the system, and then it generate a whole bunch of report for us. Okay, so here you can generate a whole bunch of report or statistics for us. If you look at output, here. Here's what we got. So you can look at these numbers. So this is a simple report that describes the strategies, and you as a trader can determine whether the strategy is good or not based on this information. Okay. So let's go back to the original code. Okay. So we can take a look at these strategies. SMA2. So we click Control P, go to the source. Now this is an event-driven programming paradigm. So basically, our strategy listens to the event that it cares about, and for simple moving average crossover strategies, we cares about the price. Okay. So basically, every time there's a change in the order book, every time there's a new price update, an event handler will be called, and this particular event handler is this on depth update. Okay. So if you want to examine it, we can put a breakpoint here. Okay. So basically, every time a new price is updated, this function is called. It will tell you the current timestamp and the order book and whatever market condition and your current existing positions. Okay. And then you as a quant trader or quant analyst coding up the strategies, you only need to program the orders. So compute orders is here. So we go here, hit Control B. This is the spirit. This is the soul of this function. Okay, it's basically computing the new orders to the market. Okay, based on the latest information, based on the new prices, it is computing a new order, and it send this order. So you see, and it send this order to the broker for execution. Okay. So to understand this more, I suggest you to actually play this in the debugger. Okay, so let's do this experiment. We put a breakpoint here on depth update to see whether it stops when there's a price update. Okay, so we go back to the demo file, we right click on it and say debug file. Okay. Okay. So you see, so as I said, whenever there's a new price update or order book change, this will be called. So you see, the price of XOM is 619 at this particular timestamp. So on the first day of our simulation, 1990, January the 2nd at 4 p.m. New York time, I see that the price for XOM is 619. Okay. And based on this information, I will call the compute order function. So it's updating the signal. This signal is just the moving average crossover signal. Okay, it's checking the crossover between the faster moving average and the slower moving average. So I can see that there's nothing. Okay, so there's no signal. Okay, there's no signal. So when there's no signal, I want to close my position. So this is my desired position, my target position. And this does not generate any orders. Okay, so you see that the order list is empty. Okay, it does not generate any orders. Okay, and then we hit F5 or we hit this run button F5 to continue. Okay, you see that when it stop, why is it not stopping? Okay, why is it not stop? Okay, let's do it again. So let's do it again. I go back here, debug. Okay, so on the first day of our simulation, I get a price. Okay, and then I step over and then hit F5. Okay, so next time it stop at this function is the next day, 1990, January the 3rd, the next day, right? Again, 4 p.m. New York time. The price changes to 613. So I hit F8 and then hit F5 again. So you see the price changes, right? 607, 603, 613, $6, 603, and the day timestamp is 1990 January the 10th. Okay, so you can sort of see that by playing this in the debugger, you can monitor the order book and see how the strategy makes its decisions. So we want to see something more interesting. We want to see when there's actually a crossover that happens. Okay, so we put a breakpoint in the for loop in here. Basically, we want to stop whenever there's a real crossover signal. Okay. So to do this, we remove this breakpoint and then we hit F5 to continue, and we stop when there's a crossover signal. Okay, and this is a crossover, and the crossover is cross above. So what that means is like we now have a faster moving average crossing the slower moving average above. Okay, so we are supposed to buy, right? Let's see. So our position is the current position is 0. Okay, and our target target position is 1. So we want to buy 1 unit. So we want to buy exactly 1 unit of XOM. Okay, so here it's creating a new market order based on the product XOM based on the desired quantity. Okay, and then the size is to buy, I think. Oh, it's not printing up, but anyway. Okay, so here you compute the order, it's creating an order. So you see this is saying buying XOM for 1 unit at price infinity. Of course you wouldn't buy anything at infinity price, right? That just basically means you buy at the market order. Okay. You see like you have at least 2 types of order when you're buying something. You can either place a limit order, which is trigger on a desired price, or you buy at the market order. So whatever the best price is, you pay for it. Okay. So this is saying buying XOM at the market price for 1 unit. Okay. And then you send this particular order to the broker for execution. Okay. So you hit F5 again. I have another signal. So this is now oh, this is 1 year later. So basically, after you get into a long position, you wait almost for 1 year, and in 1992 March 6, 4 p.m. New York time, at price 767, you have another crossover signal, and this time is crossing below. So that means that the faster moving average now cross the slower moving average below. So we want to sell. We want to get into short positions, and we see that our current position is 1. So that was this current position is due to the buy order we just sent right last time. So our current position is 1, and the desired position to get into should be -1. So what we really want is like we sell 2 unit. So you see -2 here. it means that we sell 2 units of XOM. So everyone understand that, right? Our current position is 1, so we sell 2 units of XOM. We should end up with a -1 position. So we enter into a short position of XOM. Okay. So I come back here. I can examine my orders. So it is the selling XOM at market order for 2 units. Okay. So and then I send the orders to broker for execution. So you can continue like this, and in fact you can look at this picture. So this is the buy order that we had. Okay. Because the faster moving average is crossing the slower moving average above, so we have a buy order. This two graph does not. Oh, sorry. I'm sorry. The buy order is here. So okay, it's not drawing this graph properly for some reason. Buy order is here, and then the sell order is here. You see the faster moving average is crossing the slower moving average below. So you have a sell order here. So you can zoom it. You can see the sell order. You see sell XOM at infinity. Now this is not saying infinity because it actually gives you the executed price. So when you say you want to sell a market order, it actually sell at the best price for you. So it's at 767, okay, for 2 units, and it corresponds to this crossover signal here, okay. So this is the actual executed order, not infinity. 767 was the best price when you were selling, okay. So you can continue doing this experiment. You can continue doing this experiment. It will have more crossover for the last 20 years. And then we can look at this graph. So you have like buy, sell, buy, sell, buy, sell, buy, sell, buy, sell. Okay. So everybody have any questions so far? So this is how we do. This is how we co-op our strategies in algo quant for simulation. And this is how we do back testings in algo quant for simulation. Of course, this back testing is only doing it for historical data, and we mentioned it multiple times that back testing on historical data alone is not sufficient. We want to back test it on artificial data, on bootstrapped data, and algo quant support that too. But we're going to see it later when we get into how we do bootstrapping. But for this particular lab, let's limit ourselves to historical data first. Actually, this simple moving average crossover is co-op in a very complicated way because it can be generalized into other scenarios as well. So we can try to co-op something a lot simpler. But let's understand what strategy is first. So we said that a strategy is just a event handler. Okay. So a strategy is an event handler. Okay. And in this particular case, it listens to the order book informations. Okay, so it listens to the depth update. So it inherits from here. It should stay on depth update. Okay, so basically it subscribes to in other words, it subscribes or listens to the depth signal, to the order book signal. Okay, and we wanted to plot. Basically, we wanted to plot the P&L curve. Okay. You can create your own strategies. As a strategy is basically it does two things. Okay. First of all, it keeps track of the signals. Okay, it keeps track of the signals. So in this case, it keeps track of two moving averages and check the crossover. Okay. Number one. So number two thing is a strategy sends out an orders. Okay. So let's write it down here. A strategy. This strategy does two things. Does the following. Number one, it keeps track of the signal state. Number two, it computes the orders to maintain a desired position. Now remember, we talked about last time a strategy, a quantitative strategy is just a function f here. Here, a strategy is just a function. So every time we want to determine the buy sell orders, we have to take the difference between the current desired position to take and the current positions, and then we take the difference. So this is how we compute the order. In fact, this is how this code is implemented. This is our current position. This is our desired position. So this is the math function. But in this case, it's either 1 or minus 1. Okay, and then we take the difference, and this is the orders. Okay. Um, so we can do some experiment here. We can do some experiment here to see whether our theory is correct. Like if you remember the lecture from yesterday, we discussed that like this n, the slower moving average, it should not be too big. 250 is not infinity, so this is very big. Um, so we can test out the GMA 2-1 strategy here to see whether it works better. Like remember, like this strategy doesn't work, right? 1 year versus 1 month doesn't work. So we want to try whether this works. Okay, so this is the GMA 2-1 strategy that we proved mathematically in the last lecture, and we want to do a simulation on this to see whether it actually works better on the historical data for XOM. So you see, like it's very the reason you see that is like it's making a lot of trade, so it's making too much buy sell orders. So you see, like almost every day you buy and sell, right? And then you zoom in, and it's actually losing money, even worse. Even worse than than you see here, P&L is minus 210, so it's even worse. By the way, like you see, like it's very important to have a software now. It's very important to have a software that allows you to do simulation and backtesting and experiment. Because so one thing that pops to mind is that if you do GMA21, it's making too many orders, and the transaction cost probably kills you. Okay, like when we were doing analysis yesterday, we didn't consider commission or transaction cost at all. Okay, uh, but if you are trading like this every day, then you're paying a huge amount of commission. Even though your strategy may be making money, but after commission, your strategy could lose money, a lot of money, in fact. Okay. So we can try, but we know like, but we still know that like we shouldn't use too big a number here. So maybe we do 520 and see better. So having the source code allow you to do experiments, and then it allow you to get a feeling of what your strategies are like. So programming is very important besides the mathematics. No, it's still making a lot of orders, and it seems you still lose money. Okay. So another thing you can try is that you can try another stock like Apple, for example, and it's listed on Nasdaq. Okay, maybe not from 1990, maybe from 2000. Okay, so this is just saying it's just asking the algo quant to download data for Apple from Yahoo, and then you do the simulation using this set of parameters and run it. Oh, so it's not doing anything. It's make some money and then up, and then it crash. Okay, for Apple. So you see, like this trend following strategy is not working when there's a long-term trend for Apple. You see, this is a long-term trend. But in fact, this simple moving average crossover strategy is not working. You see, there's a big drawdown here. So buy and hold works a lot better. So let's try our favorite parameters, 1 and 2. See how it goes. Okay, so this is making money. So you see that like the P&L graph follows very closely the price of Apple. Zoom it. So it follows very closely the price of Apple. But still, this is making a lot of trade. So the transaction cost probably kills you. Okay. So it's having a lot of crossovers. So for the we still have 20 minutes. For the next 20 minutes, can you try to do the following? First of all, you try to run this program by changing the parameters. So you can put in your favorite stock here, and you can put and you use different parameters for the SMA2 crossover strategies. Basically, you want to understand whether our theory is correct or not, because our theory tells us this should not be too big. Okay. So you try different numbers. So you compare 1, 2 versus 120, and then versus 1, 250, and to see how the P&L performs for different stocks. So you need to, the idea is that you need to have experiment to confirm with the theory that we discussed yesterday. Okay, so here's the software for you to play around. And more importantly, I would encourage you to code up your own strategies. Okay, so here you have a SMA2 crossover strategies. Okay, but let's code up a GMA21 strategy. So here is what you do. Okay, you go here, new class, and this is called M2M GMA21. Okay, this is the strategy that we discussed theoretically yesterday. Okay, so in order to make this strategy, you can do this. So first of all, you say this is a strategy, obviously, and it listens to the order book event. Okay, it listens to the depth event. So there are functions that we need to implement. All you have to do is you move your mouse to this line, and then you hit Alt Enter, and then you choose the first one, implement all action methods. Okay, so there you go. So the most important function here is this. Basically, you want to compute. Order based on the order book update. Okay. So GMA21, what's the GMA21 strategies? We discussed it yesterday. Basically, it's saying when the current price bigger than the last price, we buy. When the current price smaller than the last price, we sell. We enter a short position. We enter a short position. We enter a long position. Okay. So given these strategies, let's put a comment here. Okay, given these strategies, we can you try to code it up? Basically, you need a state. The state is very simple. It's just last price. Okay. Okay, and here you will see something like that. You say so you need to keep track of the current price. Current price, right? You get the current price from the order book. You can use ask the ask price, the bid price, or the mid. Let's use the mid. Okay. So basically, your code would say if current price is bigger than the last price, we want to buy. Okay. Otherwise, we sell. And then we send the orders. We send the orders to the brokers for execution. And the way you do it, you can copy from this code here. So basically, you compute the order. Okay, you compute the order. So this is null for now. So here you compute the order, and then after you finish computing the order, you send it to the or you send it to the broker for execution. Okay, so all you have to do now is to fill in the logic here. Okay, and after that you can, in your simulator, you can replace this with your strategy here, with your strategies. Okay, so can you try to do this for the next for the rest of the class, and then if you have any question, please feel free to ask me. Okay, everybody understand what the test is? Okay, so let me repeat. Number one, you play with this template by changing the parameters to see whether the theory that we discussed yesterday is correct or not. Okay, by doing some experiment, doing some backtesting on historical data. And number two, you call up your strategies. Okay, and this is the simplest strategy that you probably can. This is probably the simplest strategy that you can call up for. Okay, so this is the trading logic. And after you code it up, you can just plug and play here. Okay, everybody understand the task? So please go ahead and please page me if you have any question. Okay. Um, yeah, but this is not GMA is not using the arithmetic moving average. It's using the geometric moving average. When m equals to 1, the right hand side becomes 0. So you only need to compare the current returns with 0. This is a very uh, a special case of the GMA strategies. We use this we use this as an example not because the strategy works or makes money, but this is the simplest to analyze and to implement. So we use it as an example for education purpose. So does anyone have any further questions? Um, well, I know that you will not be able to finish the whole exercise during the class time, but I still encourage you to try to finish it offline. Um, because whatever we're going to discuss in the next 3 weeks depends on this. Okay, so we are going to do more mathematics and we are going to do more programming. So please finish this exercise so you know you feel comfortable doing strategy coding and backtesting using algo quant system. Okay. Uh, if no one has further questions, then we are finished for today, and I will see you to next week, next Tuesday and Wednesday at the same time. So it's 8 a.m. in the morning at Hong Kong time, or it's 8 p.m. New York time. Okay. So everybody has a good week. Um, Goodbye. Okay. Goodbye. Thank you very much, everybody, for your participation.